Cosmic nebulae are the cradles of light in the universe, the birthplaces of stars. For millions of years, nothing seems to happen, but gravity waits patiently. For example, when the shock wave from a supernova strikes the nebula, the balance is disrupted. Turbulence and areas of higher density form. These protoplanetary disks can reach a diameter 100 times that of our solar system. A sea of possibilities. Inside the disk, the gas heats up and begins to glow. More and more dust and gas from the surrounding area now streams toward the center. Mass attracts more mass. Gravity does its work. Beneath the surface, a giant is growing. Gravity shapes the gas into a sphere. What began as a wafer-thin veil in space is now compressed to unimaginable levels. At the center of the gas sphere, the atoms are compressed so intensely that they change their form. Pressure and temperature continue to rise until a critical point is reached. Nuclear fusion begins. Atomic nuclei fuse together. From this point on, the gas sphere generates its own energy and begins to radiate. A star is born. Can we, as humanity, succeed in artificially replicating this process? Can we ignite the fire of the stars on Earth to feed our hungry civilization?
This is one of the hardest things humanity has ever tried to do, among the hardest. And it goes to the fundamentals of everything in the universe. It's the original power source, if you want to call it that. And now we're on the verge of accomplishing it.
Dr. Alexander Bach is one of the many people around the world working on nuclear fusion. Near Munich, at the Max Planck Institute for Plasma Physics, researchers are studying the fusion process in a test reactor. Beneath the reactor vessel lie the inner workings of the 800-ton machine. Hundreds of kilometers of pipes and cables connect the system's components. The goal? To harness the enormous heat released during nuclear fusion to generate electricity. A power plant like this could supply enormous amounts of energy, similar to nuclear power plants, but without troublesome side effects like the risk of a meltdown. Unlimited, clean, and safe energy. A promising prospect. Is it all just a pipe dream?
It's no longer a question of does it work, and it's more of a question of will it be profitable? Will it make sense to use it, right? So no one's in the field anymore worried that you might build a big machine for a fusion reactor and it's not going to do fusion. That's solved, right? We know we can do that. And the question that's now on the table is, will it be affordable? Can you make everything in a way that allows you to compete with the alternatives?
Making the fusion process efficient enough to be commercially viable. That's what Alexander Bach is working on today. But it took over 100 years of research to get to this point. After all, how the sun generates its energy was a mystery for a long time. In 1919, a scientific expedition set sail from Liverpool, England. Just a few years earlier, Einstein had published his general theory of relativity. And so far, that's exactly what it is, just a theory. British physicist Arthur Eddington and his team now want to test this world-changing theory. On March 8th, the team of physicists set sail aboard the SS Anselm. Arthur is fascinated by the sun. Although people have been observing it for millennia, the veils of ignorance still shroud its true nature. The expedition aims to test Einstein's radical theory with the help of the sun. The claim, gravity is not simply a force that attracts objects. It is a curvature of space and time. If that's true, the sun's gravity should even bend the light of distant stars as that light passes close to it. But no stars can be seen near the sun, since they are outshone by it. The only chance? A solar eclipse. So the expedition travels halfway around the world in pursuit of a solar eclipse. Eddington's destination is the island of Principe, off the west coast of Africa. A second team is on the move in South America at the same time. Now all that's left is for the weather to cooperate. Otherwise, all their efforts will have been in vain. On May 29th, the moment arrives. A total solar eclipse casts its black cloak over the land. For a few minutes, the stars become visible right next to the sun. And indeed, in this original image from 1919, the stars are in a slightly different position than they normally are in the night sky. The starlight is actually deflected near the sun, to the extent that Einstein had predicted. A breakthrough in physics. Despite this success, Arthur remains restless. It is still unknown why the sun and the stars emit light at all. Back in England, Arthur's observations cause a sensation. At the same time, the chemist Francis William Aston succeeds for the first time in determining the mass of atoms using his mass spectrograph. It was already assumed that 4 hydrogen atoms could combine to form a helium atom. But Francis Aston's measurements now show that the helium atom is slightly lighter than the 4 hydrogen atoms combined. Where did the missing mass go? Arthur provided the decisive impulse. He was the first to come up with the idea that the sun might fuse atomic nuclei in its interior. The mass lost in the process is converted into energy. In 1920, he published this idea in his groundbreaking work, The Internal Constitution of the Stars. With this, he laid the foundation for modern fusion research. And Arthur Eddington went even further. He is already thinking about the possibility of one day controlling this subatomic energy and the responsibility that comes with such power.
If indeed the subatomic energy in the stars is being freely used to maintain their great furnaces, it seems to bring a little nearer to fulfillment our dream of controlling this latent power for the well-being of the human race, or for its suicide.
A century later, Eddington's vision has taken shape at ASDEX Upgrade. In the control room, everyone is preparing for the next fusion ignition. Thousands of control parameters at the facility influence the outcome, and, consequently, whether fusion will one day become efficient enough to generate electricity. Alexander is responsible for measuring plasma density, one of the most important variables. Hot, ionized gas, called plasma, rotates inside the fusion reactor. Knowing exactly how the plasma is distributed is crucial. The measuring system is located in the basement, beneath the reactor. This machine generates a laser beam that is directed into the reactor via mirrors. There, the beam is absorbed and scattered by the plasma. The nature of this scattering provides information about the state of the plasma. The measuring laser is calibrated. Everything is now ready for artificial fusion. But how is it even possible for atomic nuclei to fuse? Under the normal rules of nature, this is impossible. After all, they repel each other. So what exactly happens in stars like our Sun? What bizarre conditions can bend reality and override the rules of physics? The Sun weighs approximately 2 octillion tons. That is 2 quintillion times 1 billion tons. Or 330,000 Earths. And it consists of gas. But due to its immense gravity and enormous heat, the gas takes on a new state. It becomes plasma. Normally, a hydrogen atom consists of 1 proton and 1 electron. In plasma, the particles move so fast that they collide with destructive force. The energy of the collision is so high that the electrons are torn from the atom. Protons and electrons now fly around separately. For a star to generate energy, the protons must come extremely close together to fuse. But that is no longer possible. This is because the free protons are all positively charged and repel one another. The electromagnetic force creates an insurmountable barrier. Were it not for the quantum world with its bizarre rules. Here, the elementary building blocks are not solid bodies, but clouds of probability. Something happens that seems impossible to us. The proton disappears. It is drawn down into the quantum realm. It dissolves, becoming everything and nothing. It passes through a tunnel beneath reality, and then it reappears. Behind the electromagnetic barrier of another proton. But the journey has changed it. It transforms into a neutron. A new nucleus has been formed, deuterium. This incredibly improbable process forms the basis of all life.
How everything has to be just right for us to even exist. If the fundamental forces of the universe wouldn't work just the way they do, then stars maybe wouldn't shine and there wouldn't be energy for life to exist. And many small things get together, and if they wouldn't be the way they are, then we wouldn't be here, or at least we wouldn't be here in this form. And it's certainly awe-inspiring to think about these things.
Inside the sun, the temperature reaches 15 million degrees Celsius. The pressure is 250 billion times greater than atmospheric pressure here on Earth. This is because the sun's outer layers exert pressure on the core with their seemingly endless weight. The plasma is compressed so intensely here that the deuterium nuclei collide with additional protons and neutrons and fuse together. Through a chain of subsequent reactions, a stable helium nucleus is ultimately formed. The key point here is that the helium-4 nucleus is slightly lighter than the 4 original protons. This missing mass is converted into energy. However, it takes about 100,000 years for the released energy to reach the sun's surface. This is because the photons carrying the energy are repeatedly scattered and absorbed. They must fight their way through the extremely dense plasma along a chaotic, zigzagging path. Through nuclear fusion, the sun converts 4 million metric tons of its mass into energy every second. Thus, it becomes 4 million metric tons lighter every single second. So how can the sun be replicated technically? Nuclear fusion is a process of extremes, and the unimaginable pressure at the sun's core in particular cannot be easily reproduced artificially.
There's no atoms anymore. The nuclei of your former atoms are 1,000 times closer to each other than they are here in a solid object. And under these immense conditions, they can fuse together. It happens quite slowly. The half-life of a proton in the sun is billions of years. It takes billions of years for one to fuse, which is good for us, because otherwise the sun would have burned out a long time ago and we wouldn't be having this conversation. So things are just right for us right now. But we cannot do this here on Earth. First of all, we can't have these conditions, right? We don't have a 1,000,000-kilometer gas ball that can create the pressure. And also we don't have the time, right? I don't have a billion years to wait and sit around and wait till I have one fusion reaction. I need things to go faster. So what we can do is just right as you said, we can increase the temperature in our machines and simultaneously decrease the density. So in the machines we propose to build, the densities are much, much lower than in the air around us. They're 100,000ths of the density in the air, but the temperatures, in contrast, are 10 times higher than in the sun.
To compensate for the lack of pressure, the temperature in the fusion reactor is raised to as high as 150 million degrees. The plasma rotates inside a donut-shaped vessel. But at such temperatures, any material would melt instantly. That is why magnetic coils hold the plasma in suspension, so that it does not touch the vessel wall. But before a plasma discharge can begin, the interaction of the entire system must be prepared down to the second. In the control room, the researchers program the course of the experiment. The shape of the plasma, the strength of the magnetic fields, the amount of fuel, and the use of the various heating systems. Alexander double-checks the plasma density measurement. In the reactor next door, a tiny amount of deuterium gas is now being introduced and converted into plasma. The discharge is about to begin. For the next 10 seconds, Garching will become the hottest spot in the entire solar system. Each discharge generates vast amounts of valuable data. For example, on plasma density or the calibration of the magnetic fields. These findings enable the next major step in fusion research, ITER. Here in the south of France, the first fusion reactor on the scale of a future power plant is taking shape. It is one of the largest and most complex construction projects in the world. ITER could be the first to demonstrate that fusion can provide enough energy to generate electricity. For a fusion reactor to operate efficiently, it must be one thing above all else: large. All the research facilities, such as ASDEX Upgrade, are too small for continuous operation. That's why ITER is a massive project. 1 million components, made up of around 10 million individual parts. Many of these components are custom-made, for which there are no proven production lines. Even the slightest deviations can mean that entire systems have to be reworked or remanufactured. When work first began in 2007, ITER was supposed to generate its first plasma as early as 2016. Since then, that deadline has been pushed back by nearly 2 decades. Critical voices are growing louder. Is fusion a dead end after all? What's taking so long?
ITER is, above everything else, a peace project. ITER was dreamt up in the 1980s by then leaders of the United States and the Soviet Union, Gorbachev and Reagan. And it was in the same category as the International Space Station. So a project that brings together the world for peaceful purposes. And so the setup of ITER is not necessarily to be the most efficient, most effective scientific project. It's not, very much not. Every country contributes a little part. Sometimes even the same part is made by several partners, just so they have the knowledge to make it in the future. It's like building a car and every one of the wheels comes from a different company. No one would do this. And it shouldn't surprise us that this is not a very efficient way of doing business. But that's not why it was made, right? It's not just for fusion, it's also for peace. And some of the questions like the tritium breeding or other technical questions will be solved by this machine. And even though the answers are maybe not as fast as we would have liked them to be, we will all get them. So that's also something it's worth something.
The construction of ITER is a monumental step. From decades of basic research to a new form of energy production. It has taken humanity only about 100 years, from deciphering how stars produce their energy to the ability to technically replicate stars. Think another 100 years into the future. What will be possible then? And how will we handle so much power and so many possibilities?
A lot of people think of maybe Prometheus stealing the fire of the gods. Depends on if you're religious, I suppose, if you think there's somebody who's going to punish you for being too ambitious. I don't know if I'm a very competitive person, but as a species, we probably are. So we're definitely at the top of the food chain by now, and we have no intention of stopping. So I suppose we're going to keep grabbing or reaching for the stars, and this is just a natural next step to actually build our own personal stars and power our civilization that way. But I think it's not just in our own service, right? So maybe in the past humans have been a bit reckless with our environment as well. And we've come around to realizing that we can't destroy this planet, we only have it once. And I think fusion can be one of the tools that we use to save it, right? So ambition can be a two-sided sword. And I think there's potential that everything's going to be better because of our ambition, not just worse, like it maybe has been in the past. So I'm fundamentally an optimist, and I'm going to stay that way.